Hello everybody, welcome back to Calculus 1 online at Frederick Community College. In this lecture, we continue discussing derivatives, and in particular, we will focus on the graphical connection between functions, their graphs, and the graphs of their derivatives. Here is a quick outline of what we're going to discuss today. First, we'll talk about graphing a derivative function from the graph of a given function. Then we will talk about the connection between the derivative and continuity. And also we will discuss three conditions when a function does not have a derivative. Let me give you a quick reminder of the limit definition of a derivative function. That is something we've discussed in our previous lecture. We say that if f is a function, then f prime is the derivative function, so that the domain of this function consists of all values of x, such that this limit exists. So we're talking about the limit as h goes to 0 of the quotient, where in the numerator we have the difference f of x plus h minus f of x, and in the denominator we have h. Okay, and as you have done your homework for the previous section, you know that this is one of the forms that we can apply to compute the derivative of a function. And as we continue our study of calculus, you will see that that's not the typical way we will be doing computations. Okay, so this week we will also discuss differentiation rules when we apply rules that will produce much quicker solutions. Okay, so this is the limit definition. And let me discuss a little bit of notation that we will use in this class. The most common notation we will use is f prime of x. So this represents the derivative of a function. Okay, sometimes we can say it's y prime if we label our function as y. Okay, then we can say d dx of f of x, okay, or dy over dx. All of these things represent the same, okay, just different types of notation. All right, now this limit definition is not something I personally use, but if you see it in the textbook or maybe in another source, that's okay. All right, that's just another way to represent the derivative. Okay, what about the derivative at a point? Okay, so that would be f prime of a, where a would be a number, okay, a value that x takes, okay, in the domain of its function, or y prime of a, or another way would be something like this, dy dx, and then a vertical line, x is equal to a. So all of this is saying, let's compute the derivative and then evaluate it at a point. Okay, so this is just a quick reminder of the limit definition of the derivative function, as well as various types of notation that can be used to represent the derivative. Okay, let's take a look at the first example where we explore the graphical connection between a function and its derivative. So here you see a piecewise defined function where the graph of this function on each interval is linear, right? So we have various intervals with various behaviors. So first thing that I'm going to do is explore the behavior of this function for each interval and write down my observations. So this is what I have. The function is decreasing on the interval from -infinity to -4. Let me highlight this interval right here so you can see that the line is going down to the right, and you can also compute the slope of this line, and the slope is equal to -2. Okay, now recall from previous lecture that we talked about the derivative as rate of change. Okay, and here it is very clear what's happening, right? If we go 1 unit to the right, the line goes down 2 units. Okay, and that is represented by the slope, which is -2. Okay, what happens on the interval from -4 to 0? Well, that is where our function is constant, and it is equal to 3. And what can we say about the behavior of this function on the interval from -4 to 0? Well, it's not changing. That's what constant means. It is taking the same value for all x between -4 and 0. Okay, let's take a look at the next interval. So that would be from 0 to 2. This one right here. And this is the interval where our function is increasing. Okay, we can see that the slope is 1. You can think about it as increasing at a constant rate. Okay, 1 step to the right, 1 step up. Okay, that is exactly what the slope is. Okay, what about the next interval? On the next interval, from 2 to 5, our function is once again constant. Okay, now it's equal to 5. But as far as the behavior goes, it's not changing. Okay, it is the same for all values of x between 2 and 5. And then lastly, on the interval from 5 to positive infinity, it is decreasing. Okay, and we can see what the slope is. The slope is -1/2. Okay, as we go 1 unit to the right, okay, we go half a unit down. All right, so we can see that we have a constant rate of change on the interval from 5 to infinity. And also we can identify one of the features here of this graph, that we have sharp corners, okay, at these values right here. So at x is equal to -4, at x is equal to 0, at x is equal to 2 and 5. Okay, we can see that the function is continuous there, right? Okay, so we have continuity. There are no jumps, no gaps. But what about these corners, right? What do they represent? We will explore that idea as well. Now, this is the graph of the function. Let's go ahead and call it f. Okay, and now, based on these observations, we're going to make a sketch of the function's derivative. Okay, so the graph of the derivative will look like this. And let's see what's going on here. We've mentioned that on the interval from -infinity to -4, our function was decreasing. And notice what happens here. The function is decreasing at a constant rate of change, -2. And that is what y prime or f prime is equal to on that interval. So f prime on that interval is equal to -2. Okay, that's how we would sketch the derivative of this function for this interval. All right, what about the next interval? The interval from -4 to 0. That is where our function is constant, and that corresponds to f prime being 0. F prime is equal to 0, okay? That represented by this red line segment right here that's on the x-axis. Okay, let me highlight it. This is this one right here. That is where the derivative is equal to 0, right? It represents the rate of change of our function on that interval. Well, if it doesn't change, that means the derivative is equal to 0. Okay, next interval from 0 to 2. We said on the interval from 0 to 2, the slope is equal to 1. Okay, and that is where f prime is equal to 1 right here. Okay, so that would be this piece, and so forth. Okay, the function is constant on the interval from 2 to 5. That is represented by this piece right here for the function. What about the derivative? The derivative is going to be 0. okay? And then the last interval where the function is decreasing, that means we have a negative derivative, okay? So negative 0.5 or negative 1/2. So that would be this piece right here. So f prime here is negative 1/2. Okay, so now you can see the graphical connection between the derivative and with the graph of the derivative and the graph of the function. So everywhere where the function is decreasing, we have the derivative being negative. Okay, if the function is constant on an interval, that's where the derivative is 0. Okay, and if the function is increasing, that is where the derivative is positive. Now, notice what happens at those points that we identified as corners points. So over here, what we have in the derivative, we have a jump, right? But not only that, notice that neither one of those dots is a solid dot. They're both hollow dots, okay? And this is where the derivative does not exist at those points where we have sharp corners. And we're going to explore this idea in more detail later in this lecture. But one way to think about it is, well, what is the tangent, right? So what is the slope of the tangent line at that corner? And the answer is there isn't one. Okay, there is no way to find a tangent line that's right at that one of these corners. Okay, so the derivative at these points does not exist. And again, graphically, that is represented by these hollow dots. Okay, so we certainly don't have the derivative existing on the same domain as the actual function for this particular example. Okay, so this is your first motivating example in our exploration of derivatives, the graphs, and the connection to the functions. Let's take a look at our first example where we're exploring the connection between the function and the graph of its derivative. So we're given this graph, f of x. Notice that we don't have the expression for f. That's okay. We're just trying to get a general idea of this connection. Now, let's discuss some of the behavior of this function. Okay, notice that our function is decreasing from negative infinity to roughly -2, and also from 3 to positive infinity, we have this behavior where the function is decreasing. You can think about this as all of these slopes of tangent lines on these intervals, they will be negative, right? So negative over here and over here, okay? And that is where our derivative will also be negative, which should correspond to the graph of the derivative function being below the x-axis. Okay, now what happens between -2 and +3? This is where the function is increasing. Okay, so the derivative here will be positive. That means the graph of our f prime should be above the x-axis. Now we can say a little bit more. Okay, what happens at -2? If we make a tangent line over here, notice this is going to be a horizontal line, and we know that the slope of the horizontal line is 0. So that is where our derivative function will be crossing the x-axis. Similarly, for x equals to 3, we also have a horizontal slope. Okay, horizontal tangent line, right? And notice that also corresponds to the points where our function is changing its behavior. For the first one, it's going from decreasing to increasing, and then we have change of behavior from increasing to decreasing over here for x is equal to 3. And that is where our derivative will be crossing the x-axis as well. Okay, so f prime equals to 0 over here and also over here. Okay, so putting all of that together, we can get a sketch of our function, okay, of our derivative function f prime, and this is what we end up having. Okay, so let's confirm what we've just discussed. Okay, f prime is indeed negative on the interval from -infinity to -2, and then it's crossing the x-axis over here. Okay, then it is positive on the interval from -2 to +3, right? The graph is completely above the x-axis, and then it's crossing the x-axis at x equals to 3. All right, and then it's negative once again on the rest of the domain. All right, so this is your first example of sketching a derivative of a function just from a graph of f. Let's take a look at example number 2. Here we're given a graph of a function that looks like a polynomial function of even degree. And I can say that because both branches are going up to infinity. So I am referring to the end behavior of polynomial functions here. Okay, let's see what we can say about the behavior of this function. We see that on the interval from -5 to +3, the function is decreasing. And then from 3 to +infinity, it is increasing. So what can we say about the graph of the derivative then? Well, from -5 to +3, the derivative will be negative, which means the graph will be below the x-axis, okay? And from 3 to +infinity, our derivative is positive, which means it will be above the x-axis. Okay, what else can we say? Let's take a look at the points where we have horizontal tangent. So one of these points would be x is equal to 3. We can see that that is where we have a horizontal tangent, and that is also where our function is changing its behavior from decreasing to increasing. So for this point, we can think about it as the point where f prime will be crossing the x-axis. Now we also have an interesting situation where we have a horizontal slope right here, but notice that the graph of f in this case is not changing its behavior. It is still decreasing, okay? However, something is different. And if you notice that the way our curve is bent is different, so it's curved slightly differently on the left than it is on the right, and it is a concept that we will explore more later in the semester. And what I'm referring to here is the concept of concavity. Okay, now what would that mean for our derivative? Okay, if we have this horizontal slope, okay, our slope here is horizontal, but the behavior of the function is not changing from decreasing to increasing. Well, that means that at that point, the graph of f prime will just touch the x-axis, but it's not going to cross it. Okay, so now let's take a look at the graph of f prime. Okay, so if this is our f, then this is f prime, and let's see what we can notice here, that it is indeed negative from -5 to +3. Okay, and then it is positive from 3 to +infinity. Okay, what else do we notice? That over here at x is equal to 0, the graph of f prime just touches that point. Okay, it is equal to 0, but it's not going to cross the x-axis. Okay, and then it does cross the x-axis over here. Okay, at x is equal to 3. And you might also notice that f prime looks like a polynomial of odd degree. Okay, so f looked like a polynomial of even degree, And this looks like a polynomial of odd degree, still positive leading coefficient. So maybe your intuition is telling you something about this relationship between functions and their derivatives if we're working with polynomial functions. And if you have some sort of intuition, that's great. Let's see if your intuition is confirmed by the computations in the next section. Okay, so once we see how we can compute derivatives of polynomials, we will be able to establish this connection between f and f prime when we're dealing with polynomials. Okay, let's discuss one more example where we're sketching a derivative. All right, so on this graph, we see that on the interval from -3 to 0, our function is increasing. Okay, so that is where our f prime will be positive. And then from 0 to +3, the function is decreasing. And that will correspond to the interval where f prime will be negative. Okay, what else can we notice here? That the tangent over here is horizontal. That will correspond to the point where the derivative is equal to 0. And also, if you were to try to do tangent lines at the end points, that also looks like we would get horizontal lines. All right, so putting all of that together, let's see a sketch of our derivative function. Okay, there it is. So our function is indeed positive. Okay, so this is f prime, right? So let me mark it. So this will be f. This is f prime. Okay, so f prime is positive on the interval from -3 to 0. Okay, and it is negative on the interval from 0 to +3. Okay, and what else do we notice? That our function does cross the x-axis. Okay, so it crosses it at 0 over here, and also it approaches 0 at the endpoints. All right, so here's your example number 3, where we'll look at a graph of f and then discuss the behavior of its function, where we have increasing behavior, decreasing, horizontal tangents, and then convert it into the behavior of f prime. Okay, let's switch our focus to the next topic for today's lecture, and that is derivatives and continuity. Here you see a statement that says that differentiability implies continuity. That is, if we're working with a function, f of x, and a is a point in its domain, then if f is differentiable at a, then it must also be continuous at that point. So let's explore this idea further. First, let's take a look at the following graph. Here, I have a graph of the absolute value function, and it is fairly easy to confirm that this function is continuous for all values of x. We can see it from the graph. We could also apply the 3 conditions of continuity for each point, and we will see that those conditions are satisfied. However, f is not differentiable at x is equal to 0. Just this sharp corner right over here for x is equal to 0, the derivative does not exist. And the reason for that, well, from the algebraic point of view, is that the limit doesn't exist. And it doesn't exist because if you were to compute the right and left limit as we approach 0, they will be different values. Okay, now a more intuitive, more graphical explanation of this would be that there is no tangent. Okay, there is no tangent line at that sharp corner. Okay, thus we cannot define the derivative. So here's your first example where a function is perfectly continuous for all points in its domain. However, It is not differentiable at one point, x is equal to 0. So notice what this statement is saying. If it is differentiable, then it implies continuity, but it does not imply the other way around. So this one I'm going to cross over. Okay. And here's your first example that says that's not true. If the function is continuous at a point, that does not mean it's also differentiable. Okay, let's take a look at another example. So here I have another function. F of x is the cubic root of x. And for this function, we will see that f is continuous for all values of x. No problem here. We can apply the three conditions of continuity. And from the graph, we can see that there are no jumps, no asymptotes, no holes. Okay, but again, it is not differentiable at x is equal to 0. And from a graphical point of view, this would be represented by the vertical tangent. Okay, so if we would try to make a line that's tangent to x is equal to 0 to the graph of this function, it would be a vertical line. Okay, and the slope of a vertical line is undefined. So here is another example of a function that's perfectly continuous for all values in the domain. However, it is not differentiable at x is equal to 0. Okay, now I want to emphasize this does not contradict the statement of this theorem, because the theorem says if it's differentiable, then it's continuous. But the opposite is not always true. Okay, so in conclusion, we say that if we know the function is differentiable, we can say it is also continuous. That's a conclusion that we can come up with. Okay, it does not go the other way around. We cannot say this. This would be false. However, the contrapositive statement is true. If it's not continuous, then it's not differentiable. Okay, what does that mean? In order for a function to be differentiable, it must also be continuous, although that's not enough of a condition. Okay, so there are other things that need to be satisfied. All right, so this is a nuanced concept. Okay, take your time to really think this through. And if you still struggle with understanding it, that's okay. Reach out to me and we will discuss it in more detail. Okay, let's take a look at the three cases when we can say that f is not differentiable at a point. Now, while most functions that we discussed in our class will fall into one of these categories, there are always exceptions. So keep that in mind. You might encounter a function that's discontinuous and it's a challenging case that does not fall neatly into any of these categories. Okay, now let's take a look at the first one. It says that if f of x is not continuous at a point, then we say it's not differentiable. So that is something we discussed in our previous slide, that continuity is needed. Okay, it's a must. It is not sufficient, but it's definitely needed. If the function is not continuous to begin with, then it's not differentiable. And here is an example. For example, we have a rational function that has a vertical asymptote, looks like at x is equal to 8. So f is not defined at 8. It's not continuous at 8. It's not differentiable. Okay, so that is our first case. The second case is if the graph of f of x is not smooth at a point. Okay, not smooth, that means it has a sharp corner or a cusp. Okay, and a good example would be the absolute value function. So here I have a function that's shifted. Okay, it's the absolute value function that's shifted some points to the right and up, and looks like at x is equal to 2, it is not differentiable. Okay, so notice it is continuous, but because we don't have a smooth curve at that point. We have a corner. It is not differentiable. Okay, and then the last case is if there is a vertical tangent line at that point. Okay, so that would be something like this. Here I have a function that's a cubic root. Okay, it's perfectly continuous and the graph is smooth. Okay, however, at x equals to 4, we have a vertical tangent. So this is where our function is not differentiable. Okay, so 3 scenarios: if f is not continuous, if the graph is not smooth, and if there is a vertical tangent line, then we say our function f of x is not differentiable at that point. I'd like to finish this lecture with the discussion of problems that you might encounter on your homework where we need to use critical thinking and understanding of the definition to answer some questions. Okay, so it will look something like this. We say that we have a function f of x that is continuous at x is equal to 4. So that's a given condition. We also have the value of our function at 4. Okay, f of 4 equals to 7, and also f prime of 4 equals to 1. Select all statements that must be true. So let's go through each statement one at a time. Okay, the first one says f of x is differentiable at x is equal to 4. Is that statement true? Yes, this statement is true, and it is justified by this expression right here. It's given to us that f prime of 4 does exist, and it is equal to 1. Okay, so this statement is true. Let's take a look at the second statement. This one says limit as x goes to 7 of f of x equals to 4. Well, this is certainly not true. Okay, well, it could be true, but we can't say this just from this information because we don't know what the function is. Okay, but just based on the information that's given to us, we cannot claim it. Okay, so limit as x goes to 7 of f of x equal to 4, no, we can't say that. Okay, what about limit as x goes to 4 of f of x equal to 7? Now this, we can say this is true. Okay, and why is that true? This is true because we have that the function is continuous at x equals to 4. Notice that here we have x is equal to 4. Okay, and f of 4 is equal to 7. Okay, so if the function is continuous at the value of 4 and the value of our function at 4 is equal to 7, then the limit must be equal to 7. That is one of the conditions of continuity. So we would say this is also true. And this last one is not going to be true. I believe it's never true for these problems. So none of the above, no. Okay, so that's what you would do here, and let's check. Yes, that would be the answers that you would select for this problem. So you might encounter something very similar to this. Carefully go through each statement and see if you can apply your knowledge of the definition of continuity and function being differentiable at a point. Let's take a look at the last example for today's lecture. Here we're given the following limit. Limit as h goes to 0 of the quotient f of -7 plus h minus f of -7 divided by h, and that is equal to 9. So this is saying this limit does exist and it's equal to 9. Equivalently, we can say f prime evaluated at -7 equals to 9. Okay, so this is how we would interpret this expression. All right, let's take a look at all the options that are given to us. The first one says f of x is continuous at x equals to -7. Is that true? Well, let's see. We just discussed the differentiability of our function at -7, right? F prime of -7 does exist, so the function is differentiable and therefore it is continuous. Okay, so this is the theorem that we discussed in this section where we say if f is differentiable, then it also must be continuous. Okay, so that is true. Let's take a look at the second statement. This one says f of x is differentiable at x equals to 9. This statement might or might not be true. Okay, we cannot say for sure based on the information that's given to us, because here we're only told that f prime at -7 does exist. Okay, so we can't say for sure. We're not going to select this as a statement that must be true. All right, let's take a look at the next statement. That one says the limit as x goes to -7 of f of x exists. Well, let's see, what can we say here? We're going to refer to what we've already established. F prime at -7 exists. That's given by this limit right here, okay, which implies continuity of this function at -7, and that means this limit also must exist because it is one of the three conditions for a function to be continuous at a point. Okay, so what is our justification for this one? It's because this statement is true. Okay, let's see. What about the fourth statement? Limit as x goes to -7 of f of x is equal to f of 9. Okay, we cannot say that. This might or might not be true. Okay, but we can't say that for sure. All right, we just know that that limit does exist. We cannot tell from the information that's given to us what it must be equal to. So that's one of the statements that we're not going to select. And of course, none of the above is also not something we will be selecting. Okay, so in this case, you would select statement 1 and statement 3. Okay, so we're gonna go ahead and stop right here. Thank you for watching, and I will talk to you next time.